Now, can you extend this same thing to an n input NAND gate? Right? Y equal to A1, A2, AN. First, draw the circuit, get the sizes right, then evaluate the delays. And only propagation delay, okay? So what's the size of the PMOS transistors for an n input NAND? All 2, no change there. Right? For a NAND, it doesn't matter how many inputs, PMOS is always 2. What's the size of the NMOS? N. So what's the total output capacitance? 3N into C. What's the intermediate capacitance of each of those nodes? NC. They are all shared uncontacted diffusions. NC. Okay, so the rise, let's first do the rise propagation delay. Rise is very simple. What is the answer? 3. Let's also draw the equivalent circuit. It's basically a single R with 3NC, right? Therefore, rise delay 3NRC. What about fall? So let's get the equivalent circuit right first. I have 3NC. What's each resistance in this network? R by N. Going to a capacitance of NC. R by N. And so on. So what do you get as the final answer? You will get 3N 3NC, right? 3NC into R plus NC into N minus 1 by, no, I have R by N and I have N minus 1 of them, right? So N minus 1 R by N, correct? Plus NC into N minus 2 R by N and all the way down to NC into R by N. So what does this evaluate to? Yeah? N into N plus 5 by, oh, N plus 5 by 2, okay, sorry. Is this correct? Okay, go back and evaluate it. That's not the point of the discussion here. So what is it that you note? Whole by 2. Yeah, right, that's what even I thought, but doesn't matter anyway, that's beside the point. Go back and check the answer. The key point to note is that this delay, by the way, is called the parasitic delay of the gate, because this delay is coming in because of its own capacitances. It's not that we have added any load capacitance to this gate. Just because of its own diffusion capacitances, right? Think about it, we have not considered even one gate capacitance here, right? That is what will form the load capacitance from the next gate. These are all just diffusion capacitances from its own layout, and that grows as N square. Okay, or maybe I should say N square, but I used N. Delay grows as N square, and therefore it's not a very good idea to make logic circuits with more than 4 input NAND gates or 4 input NOR gates. If you want to make a 6 input NAND gate, then you split it up as 2 3 input NAND gates and then combine them appropriately in the logical logically correct way, right? So the key conclusion here is, do not stack more than 4 transistors in general, okay, PMOS or NMOS. PMOS will actually be worse, okay, doubling the capacitance, everything, okay. You'll see later there are other reasons also why we should not do this. Therefore, it's generally a good idea that people stop with 4 input NAND gates, okay. Typically 3 is preferred, but at most 4, not more than that, okay. So now let's proceed with another interesting thing, because it's not possible for me to achieve the timing that I want on the circuit with just these unit gates. When I say a unit gate, let me define what I mean. Unit gate. So for example, a NAND 2 2, 2, 2 and 2. This is what I call a unit NAND 2 gate. Just like the reference inverter where we had the size of 1 and 2, for the NAND I am saying the unit gate is 2, 2, 2, 2, all sizes. For a NOR it will be 1, 1, 4, 4, which is my unit gate, right? These gates unfortunately are not sufficient to solve my timing purposes, timing constraints, because they have limited driving capability. The current is limited by the fact that the width is 2, right? There is only so much current that it can deliver, and therefore it cannot be used, for example, to charge a very large load capacitance. Therefore, we need to do something known as gate upsizing. We will upsize a gate by a factor of k. So what does that mean? I will simply say that I increase the size of every transistor on this logic gate by a factor of k. So I'll make this 2k, 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 2k. Okay. Now I want you to calculate the 4 components of delay for this configuration: rise, fall, propagation, contamination, delay. Before we do that, can you tell me what the capacitance on each node is? What's the capacitance on the output node? 6 kc. What's the capacitance on this node? 2 kc. Very good. Yeah. Now can you tell me the delay? So for rise delay, what's the value of each resistance of the PMOS transistor? R. So you get 2R by 2K. So you get R by K. R by K. And this is, what about the NMOS? R. R by R by 2K. It's only for the PMOS that you have to do 2R by W. For the NMOS, it's just R by W. So do all of you get these 4 equivalent circuits first correctly? Okay. So now tell me the delays numbers here. Contamination rise. How much? 3 RC. Here. Fall. Contamination fall. Propagation rise. 6. Propagation fall. RC. What is the key conclusion you get from this? Parasitic delay to a first order is independent of the gate size or the gate drive strength, because this thing of sizing it up by a factor of K is making it a stronger gate. You are giving it more drive strength. But parasitic delay is independent of drive strength. So parasitic delay is independent of drive Why is that? Because when I upsize a transistor, the capacitance goes up by a factor K, the resistance falls exactly by the same factor K, and it's RC, which is the delay, and therefore they cancel out. To a first order, this is true. Okay. Now because of that, the fact that it does not depend on delay, what we do is we do not worry about all this contamination delay and all that stuff. We just simply look at the output approximation simply count the output diffusion cap, let me say. Okay. So if I have, for example, NAND 3, what is the net cap here? 3, 2, 2 and 2. Huh? 9C, right? You count the output diffusion cap and simply divide it by the cap of a reference CMOS inverter. You will get the, right, this is my reference CMOS inverter, 1, 2. Capacitance, output diffusion capacitance is 3C. So you basically just count the output diffusion capacitance of the logic gate and divide it by the diffusion cap of your reference CMOS inverter. You will get the normalized parasitic delay. Okay, what I am saying is, instead of that 7 RC, I am just saying make it 6 RC. It doesn't matter whether it's 7 or 6, because when I upsize the gate, it does not change. That number doesn't change. In some sense, when I do gate optimization later, you will find that this parasitic delay is just a constant addition and it does not alter any of my gate sizing algorithms. And therefore, I don't need to worry about these gory details when I am doing my calculations, whether it's contamination delay or propagation delay or whatever. So it's a very reasonable approximation to make that as follows. Count the diffusion capacitance on the output node and divide by the diffusion cap of a reference CMOS inverter. You will get the normalized parasitic delay, right? And normalize to cap of a reference inverter. So the delay will simply be, for this will be 9C by 3C equals 3. What will it be for an AND 2? 2, right? So for you will get 6C by 3C equals 2. So we are not considering that case where the propagation delay had that 7 RC. We are saying effectively it is just 6 RC. Okay,